Good afternoon. So I'd like to welcome you. So I'm Michel Gomez. I'm the department head in mathematics, as quite a few of you know. And I'd like to welcome you to the 2026 Simons Lections. And they will be given by Boaz Klartag from the Weizmann Institute in Israel. And after a long journey, he made it to Boston to deliver the lections. The Simons Lections were started exactly 25 years ago, thanks to a generous gift of Jim and Marilyn Simons, whose philanthropy to mathematics and other related disciplines has been pretty amazing. And we're also in the Simons building here at MIT, and so it's we over the years we've been able to have pretty amazing sets of lections, and this year will be again the same thing. So as Boaz mentioned, he was looking at the list of lections and he said, "Oh, Gregory Perelman gave the Poincaré conjecture theorem lecture." So a while ago. So that was, it's always quite interesting. So last year we had Marina Ziazowska gave the one of the set of lectures, and she spoke about sphere packings and in dimension 8 and 24. And so today we're going to go to much higher dimension, but still sphere packings. And in general, in the three lectures, so Boaz is an expert in high dimensional geometry and often combined with random phenomena and especially convex geometry. And so that's going to be some of the topics of the talk. So please welcome Boaz.
Thank you, Michel, for. Thank you very much, Michel, for the introduction. I'm really happy to be here at MIT. Michel, I'm indeed going to give 3 lectures on geometry in high dimensions. The 3 lectures are going to be relatively independent of one another, a bit of relation between the second and the third lecture. And indeed, today I'm going to discuss sphere packing in high dimensions. And I'm grateful to Barak Weiss for introducing me to this subject. Just before I start, let me encourage you and urge you to stop me at any time and ask questions or make comments. It is completely possible. You don't have to wait until the end. You can also ask at the end. But it will make the lecture more interactive and more interesting if people ask questions whenever something is not clear, whenever you have something to say. Please stop me and make this comment. Okay, so what is sphere packing? I'm afraid that not all of you attended Ziazowska's lecture last year, so I need to remind you. So sphere packing in Rn is a collection of disjoint Euclidean balls, all of the same radius. For instance, if you want, you can assume that all of the balls have radius 1. That's completely legitimate. My balls will be open sets, so without the boundary, okay, in this lecture. Now, if a sphere packing is reasonable, then it has a density. What's the density of a sphere packing? Just take a large box in Rn and measure what's the proportion of the volume of the box which is being filled by the balls of the packing. And as the box tends to infinity, sometimes this density tends to a limit, this proportion of volume tends to a limit, and that limit is called the density of the sphere packing. In this lecture, we are interested in the maximal density of a sphere packing in Rn. And this is a different question in each dimension. Let's begin by explaining what's known about, let's begin by discussing the case n equals 2. So what you see here is an example for a circle packing we see in n dimensions. Okay, disjoint balls all of the same radius. Colors mean nothing, just for beauty. This circle packing is just a part. So I'm thinking about the circle packings that extend indefinitely in all directions in a periodic manner. So this is just a part of it. But in MAD, this is infinite all directions. And that circle packing is called the hexagonal circle packing. And why is this so? Because each circle has 6 neighboring circles. And if you look at the centers of these 6 neighboring circles, these are the vertices of a regular hexagon. So that's why this is called the hexagonal circle packing. What else can you say about this circle packing? You can say that there are like little holes between the circles. And if you count, you would see that there are roughly twice as many holes as you have circles, roughly. Also, you can see many clear patterns. If you look at the centers of the balls, you can see many lines, parallel lines, and there's a very clear pattern in this circle packing. And in fact, if you look at the collection of all centers of circles in this packing, you get a lattice in Rn, in R2, sorry. So the collection of centers form a lattice. What's a lattice in Rn? A lattice in Rn is the image of the collection of integer vectors of z to the n under some linear transformation which is invertible. Okay, so in this case, you can take a shear transformation. You can keep the x-axis and kind of move parallel lines, let's say, to the right in a proportional way. This is why it's a lattice. So there are many. The map T is not determined by the lattice, but there's an important invariant of each lattice called its covolume. So if you know lattices, the covolume is the volume of the fundamental cell, and it's also the absolute value of the determinant of the linear map T, such that L is dt of z to the n. So this is circle packing where centers are a lattice. And it is known for long time that this is the optimal circle packing in dimension 2. It has an optimal density. And the density is roughly 91%. So we cover roughly 90% of the plane, and this was known, this was proven rigorously by Thue and Feyerstoss in the 20th century. So this is about the planar case. And in general, there is a particular class of sphere packings that are particularly interesting for us, which are lattice sphere packings. So this is a sphere packing where the centers form a lattice in Rn. And in all dimensions where we know the optimal density of a sphere packing, there is a lattice sphere packing that attains the density. Let's discuss the case of dimension 3. In dimension 3, there are two different lattices that attain the optimum. The optimum is roughly 0.754, this number here. And these two lattices are called FCC and HCP. And let me tell you how to construct them. So there's many ways. One way is to look at, okay, so think about layers, and each layer would be just the hexagonal lattice. So you can take layers of hexagonal lattice, but with balls, not with circles. And then you put the next layer in the holes between balls in the first layer. And if you have just two layers, there are no degrees of freedom. Every arrangement is equivalent to another by linear transformation, by rotation. But when you put the third layer, because there are twice as many holes as there are circles, as there are balls, there are two possibilities. Okay, you can either go back to the original layer, or you can have something else, and this is the HCP and FCC. Okay, the density is 74% roughly in 3 dimensions, and there are many materials in nature where the arrangement of atoms correspond to these lattices. So each material can choose, okay, there are also other options, BCC, but many materials choose to have those atoms, HCP or FCC. A nice example is cobalt. Cobalt appears in these two lists because at some temperatures, the atoms up to roughly, I think, 700 Fahrenheit, the atoms of cobalt are at one of them, this arrangement, I think the HCP, and then at this temperature, there is a phase transition, and above it, the atoms are at FCC, and this phase transition preserves the volume because these two lattices have the same density in R3. It was proven, so the problem of finding the optimal density in R3 goes back to Kepler and to Gauss, and it was proved by Hales, using also ideas of Young, at the end of the 20th century, the computer-assisted proof that this indeed gives you the optimal density of sphere packing in R3, and I think this is till today one of the two achievements of computer-assisted proof together with the 4-color theorem. We are still waiting for 21st century theorem, which is of this scale of importance from computers. It could come. Okay, dimension 4, 5, 6, and 7. it's an open problem. I mean, we don't know what's the optimal density of a sphere parking. But in dimension 8, there is a remarkable object which is as nice as the hexagonal lattice dimension 2, which is very canonical. The E8 lattice is it is a very large symmetry group. It has a perfect kissing. So if you look at all balls adjacent to a given ball in the packing, it's a tight configuration where you cannot move anything. It's not true in dimension 3. And it was proven by Blichfeld in the 30s that this E8 lattice gives you the optimal lattice sphere parking in dimension 8. But then Marini Wiazowska, who gave the Simons lectures in 2025, she got the Fields medals for proving that this is indeed optimal among all sphere parkings, not just lattice sphere parkings. This is about dimension 8. Now, in the days of Blichfeld, I think that this problem of sphere parking was mostly a theoretical problem related to number theory, to quadratic forms. But some connections began to emerge in the 20th century with the developments of, for example, of computers and communication and digital coding. So if you look on some models of communication, like say a Gaussian channel by Shannon, then you want to encode some discrete messages and broadcast them, and you encode them as vectors in Rn. And the model of the noise is L2, so you want to have the messages as vectors in Rn, which are as far as possible in the Euclidean metric. So it's nice to have these joint Euclidean balls that you can correct the errors. So that's one reason why sphere parking became more fashionable. Also, there are other models, the Hamming cube, like that. And there are also connections to group theory to find simple groups. And as part of this development of 20th century, John Leach discovered in 1965 another remarkable object, which is named after him, the Leach lattice. So this is a highly symmetric lattice, again, high kissing number in dimension 24, okay? It's related to Golay codes in coding theory. And Kohn and Kumar proved that this is optimal among all lattices, and then Kohn, Kumar, Miller, Radchenko, and Wiazowska proved that it is optimal among all sphere parkings in dimension 24. Okay, so these are all dimensions where we know the exact answer. There was dimension 2, and then 3, 8, and 24, and that this is the end of a list of dimensions where you actually know the exact answer. You can notice that the density itself seems to decrease in dimensions, so 0.74, then dimension 3 is 0.25 dimension 8, then 1/500 in dimension 24. So you can think that this is a rather small number, 1/500. It's a very low density. The spheres do not cover much of the space. But for me, as kind of someone who was training high dimensional geometry, I was surprised that this is too large. Why is it too large? Because the density is exactly the volume of the unit ball in 24 dimensions. And the volume of the unit ball in n dimensions is a tiny number. So I mean, let me write the volume of the unit ball. If you do there is a formula, but the asymptotics is roughly square root of 2 pi e over root plus liter of 1 over root of n to the n. So its volume decays much faster than exponential in dimension n. So I would expect it to be much smaller than, for example, 2 to the minus 24, which is 1/16 million. So the fact that it's as large as 1/500 was a surprise for me. So this number, you can either think of it as too large or too small. Okay, asymptotics in this business take time to materialize about the volume 24-dimensional ball. Okay, so I already used this notation. Let me have two types of densities, so delta n and delta bar n. Delta n is density of lattice sphere parking, so I assume lattice. And delta bar is any sphere parking, so it's a priori, it could be larger. Okay, so I hope it's not too confusing. Tell me if it's, okay, so they are sometimes equal, but say Rogers conjectures that they are not always equal. We don't know. There is a trivial upper bound, a trivial construction, a trivial upper bound for the density, lower bound for the density of an arbitrary sphere parking. So delta bar is at least 2 to the minus n. How come we know that? In fact, if you take any maximal sphere parking in any dimension, its density is as large as 2 to the minus n. So if you have a sphere parking such as you cannot add one more ball, what does it mean? It means that any point of space is of distance at most 1 from some of the balls, otherwise you could add a ball. Or if you want, it's distance at most 2 from one of the centers of the balls. So if you scale all balls by a factor of 2, they cover everything. So after you scale by a factor of 2, the density is 1, which means that before you scale by a factor of 2, the density was smooth to the minus n. So just you pick ball, you get this trivial lower bound. Okay, this is something which is known in dimensions. Another thing that is known about these numbers is that in the lattice case, it is possible to go over all local minima, local maxima, and find out the exact values for lattice sphere packing. So this is known in dimension 4, 5, 6, and 7. And recently, in this summer, on Archive, was posted a paper by Sigrid and Weizmann, which does in dimension 9 by inspecting 2.2 billion candidate lattices for being optimal. And okay, so this is what's known about these numbers. Exactly. However, there are many conjectures and bounds, and there is this a collection of articles, a book by Conway and Sloan, which has many tables and stuff like that. There have been also work by physicists on this problem. So Parisi and Zamponi did many things, and in particular, they looked at statistics up to dimension 50. And they write that the statistics seem to suggest that if you scale delta n by 2 to the n, this makes sense. Because of this lower bound, somehow it makes sense to scale a little delta n by 2 to the n. It's kind of common in this business. So 2 to the n delta n, they claim that the statistics seems to indicate that this grows exponentially in dimension n. But then they write that it could be that the statistics is just a pre-asymptotic effect, and that in later dimensions, things behave differently, and we saw that already in the example of the volume of the Euclidean ball. So statistics in this business, asymptotics takes time to materialize. Okay, there is another reason why we want to scale delta n by 2 to the n, and that's because if you scale delta n by 2 to the n, you get a quantity with a geometric meaning. Let me just not to forget, so my notation will be on the board, because these are things that people can forget. And so delta n is just 2 to the n times delta n, and if I ever write delta n bar, it's the same as 2 to the n times delta bar n. Okay, so this is smaller than this. Capital delta n has a geometric meaning. What's the geometric meaning? It is the volume, the largest volume of an ellipsoid centered at the origin, which is integer free. Integer free meaning that it does not contain any integer vector except for the origin. Okay, so if I want to draw it, then I have the integer lattice. Okay, this is the integer lattice. And this is the origin. All ellipsoids are centered at the origin. Okay, and for example, the unit ball is integer free. My ellipsoids do not contain the boundaries are open sets. So the unit ball is integer free, but its volume is really tiny, right? It's not a good contender. And maybe there are ellipsoids that are bigger like that are integer free and have a larger volume. Okay. Now, why? Why do we know that capital delta n is indeed the maximal volume of an ellipsoid that avoids all integer vectors? That's because roughly the same argument I said a few minutes ago. So by this trick of scaling by a factor of 2, you see that if you have actually any convex set, centrally symmetric, or any ball B, then the collection of balls scaled by a factor of 2 centered at the lattice vectors are disjoint if and only if, after you scale by a factor of 2 and get the ball itself, it is L-free. It does not contain any points from the lattice except for the origin. Okay? So this is true for any lattice L and any ball B. And now you can apply linear transformation. We said that any lattice is the image of z to the n. So if you apply transformation, L becomes z to the n, the ball becomes some ellipsoid, and you see that this is this quantity. Okay, any questions? Okay, very easy, maybe. Now, so what's this number delta n? We need to find an ellipse. It's the same problem, finding good sphere packing, lattice sphere packing, and finding ellipsoids that avoid all integer vectors is the same problem. And the unit ball is really a bad contender in this business. And nobody knows to have an explicit contraction that does that is close to the optimum. However, there are probabilistic arguments, and Minkowski at the end of the 19th century, and also Hlavka proved that delta n, capital delta n, is at least 2 plus little change. So there is some ellipsoid avoiding all integer vectors whose volume is at least 2. but the construction is random, okay? And there is a list of open problems by Peter Sarnak from the year 2000, and problem 10 in his list is to find a non-random, an explicit construction of such an ellipsoid. There is nothing that does not go to zero really fast right now. And I'll explain to you actually, the proof in Klartag is really beautiful, and I'll explain to you in this lecture that proof. Okay, so at the beginning of the end of the 19th century, it was known that capital delta n is at least 2. And then progress happened, and Rogers in 1947 improved that estimate for sphere packing by a factor of n. So he showed that there exists an ellipsoid whose volume is n, that is integer free, constant times n. I'll say a few things. First, I'll say a few words about the proof by Rogers when I go to the proofs part of this lecture. The constant, see here, it's a universal constant, and it was the subject of an investigation along the years. Rogers and Davenport got first 2 years and 1.67. Schmidt gave another proof, so as I told you, the proofs are usually probabilistic in this business. Schmidt gave a proof that analyzes very rare events, some events or some kind of Poisson-type process, let's say, and does not contain any point in some large region. So this is an event with probability e to the minus n, but still was able to work with these rare events and prove that it's positive probability and construct a good ellipsoid. This was Schmidt's idea, and we'll use this Poisson heuristic in this lecture. Then in 1992, Boll improved the constant to roughly 2. And for that, he used Bank's solution of the Tarski-Planck problem. Let me tell you what it is. A Planck is a region in space between 2 hyperplanes. Okay, that's a Planck. And the Tarski problem was to show that if you have any convex body and you cover it by finitely many Plancks, then the sum of widths of these Plancks is at least the minimal width of this convex body. So this was proved by Bank, I think in the 50s, and was used by Boll to construct lattice sphere packings. Okay, then Stephanie Vance in 2011 improved the constant to 6/e, which is more than 2, but only in dimensions that are divisible by 4. And why only dimension divisible by 4? Because she used lattice, random, everybody used something random, but she used quaternionic symmetries. So only some random construction which has some quaternionic symmetries, and she got an improvement in the constant. And then Venkatesh picked up on this idea of having some algebraic symmetries, but used much more sophisticated and algebraic symmetries using cyclotomic fields, and got a much better constant. So in sufficiently high dimension, he got more than 60,000. Moreover, he proved that on some specific dimensions, okay, so there are some dimensions where you can get log-log improvement. So this was the first deviation from this Rogers bound, and he got the delta n is at least n log n times a half. And then this 1/2 was improved to 1 by Gargava and Vyazovska in 24. Okay, so this is the history of this number delta n. Another thing that Venkatesh did, which is quite daring, but actually actually also very interesting. So he posed a conjecture. His conjecture was that capital delta n grows polynomially in dimension n. So it could be like n to n cube, n square, something like that. This is from his paper. This means, this conjecture would imply that at least for lattice sphere packing, if you want lattice packing, sphere packing that whose vertices, whose centers are form a lattice in R, for lattice sphere packing, you cannot improve by much over the kind of the greedy bound, the trivial bound for sphere packing, which is 2 to the minus n. So you would get that the optimal density of a sphere packing of a lattice sphere packing in R is just say n squared times 2 to the minus n and not more than that. And I'll discuss the reasons why Venkatesh wrote that this is a conjecture. Okay. Now, what about non-lattice field packings? So general field packings, they are less accessible somehow. So we don't have, at least historically, we do not have that many ways to construct and analyze and prove stuff about field packing which are not at least periodic or even, lattice periodic, something of this sort. But still, there was some new ideas that in the 21st century emerged. So Krivlevich, Litzin, and Vardy, they used graph theory and got a new proof of the Rogers bound. Then something interesting happened. So the physicists, Parisian and Zamponi, pretty much initiated a study in the physics community of this problem, okay? And in their works, they applied the replica method from statistical physics. The replica method is a very successful theory in statistical physics. Parisi got the Nobel Prize for it recently. But it's a non-rigorous method. And in their papers, Parisi and Zamponi, it's not a conjecture, not even a prediction, but they describe some scenario under which the density of delta bar n, the density of the best field packing in Rn, goes like n log n. Okay, this was the conclusion of some computations, very non-rigorous. You have a Taylor series and things which really okay. They did some things and got this n log n. There are many follow-up works in the physics community after Parisi and Zamponi, and you can find all sorts of numbers and predictions showing up. There is some survey paper by Zamponi summarizing the paper is about the fate, called the fate of fucking high dimensions, and in that physics paper they describe three main scenarios about what's the density of a sphere in n dimensions. Scenario A is n log n. Scenario B is polynomial growth. It was a bit so it was n to the psi, or psi is not certain. There are several options for this number, times log cube n. That's scenario B. So they are committed about the log, but there are debates about the exponent. And scenario C, so scenario C is exponential. This is the main scenario, at least in that survey paper. And okay, I'm sure I'm doing injustice. I could not survey of the physics literature, and I cannot find my hands and legs in that. I don't know. I mean, yeah, you can say also, you can say in cube and many things you can find. And okay. However, the physicists influenced mathematicians. So Campos, Jensen, Michelin, Sastra, Buddha were influenced by Parisi and Zamponi, and their ideas about amorphous packing. So basically, to put balls in a sack and kind of shaking it a bit and see what you get, and maybe that could be the optimum in higher dimensions. In dimension 3, it's not optimal. And thanks to this work by Campos, Jensen, Michelin, Sastra, Buddha, it was proven that delta bar n is at least half times n log n. Okay, so they use mathematical methodology, which is much more difficult than the physicist methodology, and therefore they prove the prediction of the physicist up to a factor of 2, or prove the scenario, the possibility up to a factor of 2. So this was in 2023, 3 years ago. And this was actually the first time in history of this problem that non-lattice sphere packings were considered, had the world record of density. But this situation could not be tolerated by the lattices for long, and our result is that the density of the optimal density of a lattice field packing grows at least quadratically with n, so at least n squared. Okay, so this rules out scenario A from this physics paper. Okay, so let me reformulate our main theorem after some linear transformation. So if you have let K in Rn be a Euclidean ball center of the origin whose volume is at most n squared, then we can find there exists a lattice of covolume Y in Rn, which avoids all points of K except for the origin. That's the result. Why did we use the letter K to denote the Euclidean ball? That's because in convex geometry it is common to denote a convex set by k, because in German convex starts with k, maybe. And we conjecture that this theorem should be true if you replace the assumptions that k is Euclidean ball by any assumption that k is any origin symmetric convex body. Kind of up to a constant, you'd expect that balls would be the hardest to pack. Packing cubes is easy. Cubes are packed with density 1, right? And somehow the Euclidean balls perhaps are the hardest to pack, at least up to a constant, not really hardest to pack. And Schmidt proved the analog for Rogers result in this context, so prove Schmidt that this is true if you replace n squared by n. So indeed, there is some grounds for this conjecture. This is about lower bounds, about constructions of good sphere packing in high dimensions. Now, what about upper bounds? What do we know about limitations of the density of sphere packing? Yeah, please, thank you.
It's like existence theorem, like there is, you need to produce one lattice in every dimension.
Yes.
But the proof is still only non-constructive, so you don't produce.
There is randomness. You flip coins in the construction. You flip coins in the constructions.
Can you repeat the question?
So I was asked, you need to produce a lattice in each dimension, but it's not explicit. So what does it mean? Non-explicit meaning that the construction depends on randomness. So you flip coins, and the randomness gives you the lattice, and nobody knows how to do it without randomness, kind of to give a formula or something like that for one good lattice, or one good, even non-lattice, and one good sphere packing. That's completely open. Please.
Venkatesa's conjecture, I guess, is wide open in terms of the polynomial bound. But here, I guess you were saying that this theorem holds even if you just have a convex body. Is that right?
Or conjecture, I don't know.
Oh, you don't know. Okay. So are there any upper bounds? Like if K is allowed to be a convex body, and its volume is gigantic, like n to the 100, can you say that there isn't a lattice? So somehow when you look at that generalization, that is not necessarily an ellipsoid.
Okay, so for the cube, you can get an optimal density. Right? You can pack cubes or parallelepipeds with density 1. So for some convex bodies, all you have is the trivial upper bound. So you need to think of some class of convex bodies, some assumptions to have some meaning for upper bound. So there's no like one sentence that I can answer you. It's more of more general than that. For LP balls, you can have upper bounds, things like that. Upper bounds, there is a really nice paper about, so there is a beautiful 4-page paper by Blichfeld from 1929 in English, where he proves a non-trivial upper bound for any sphere packing in Rn. So the density of sphere packing is never more than 0.71 to the n. Okay, just kind of, it's a precursor for linear programming that was not fully developed at the time, in the 1920s. And there were constant factor improvements by Rankin and Rogers later on, this nice proof by Blichfeld. Then linear programming became a serious subject in mathematics, and afterwards, Kabatiansky and Levenstein in the 70s improved the exponent, so it's not 0.71 to the n, but 0.66 to the n. And there were improvements by constant factors by Cohen, Zhao, and Sardari and Zargar recently. And as I was told, there is some debate whether delta n should grow exponentially or polynomially. Venkatesh conjectures polynomially. Let me give you some arguments in each direction. So why would you believe in exponential growth? By the way, I only make conjecture about delta n. Not delta bar, I don't understand at all. For delta, I feel slightly that I know something. For lattice things, but for non-lattice, it's really hard. So for lattice sphere packings, do we believe in exponential or polynomial? So exponential, why? Exponential statistics low dimension, if you look at the curve, it goes up really fast. That's clear. Second, there are other problems for which you have very specific algebraic constructions of lattices which are kind of too good to exist. For example, you can have very large Kissing number, like more than polynomial in some lattice that is kind of sort of FFT lattice, some tensor product of a small. So there are things which would not exist by random constructions somehow, which do exist. So maybe something like that should also occur for the question of packing. And also there are some analogous problems. For example, if you do some discrete problem in a finite field, FQ to the n, for the Hamming cube, for Q equals 2 is exactly the same as Rn. But for Gilbert Vershamov is Minkowski-Hlavka, really everything are analogous, but for large Q, there are some codes that have exponential improvement in that problem. So these are arguments in favor of exponential growth. Now let me tell you why Venkatesh and others, maybe me, believe in polynomial growth. That's because of the following thing. So if you look at the space of lattices, has a kind of space of it's a manifold of finite dimension. It has kind of cusps and bulk, and you have a function lambda 1, the length of the shortest vector on this space of lattices, and now so all of these algebraic constructions usually the cusp, the regions that are have very little volume and are kind of very special. But lambda 1, you know, the size of the shortest vector, which dictates the packing density, this lambda 1 vanishes at the cusp. So you don't quite, I mean, it's clear that a lattice that does a good job in packing should be from the bulk. So maybe it's kind of a random lattice because we don't know that much about the bulk. And now, this function lambda 1, maybe just some kind of random function, like many little hills, things like that. And the heuristic of Venkatesh is something along this line. So the space of lattices is dimension roughly n squared. So to discretize it, you need e to the n squared log n points, something like that, right? Not that more than. And let's say that each of them is kind of, and if the function is kind of random, then you basically have like e to the n squared log n experiments. And each of them, you get a random lattice and you see what's lambda 1. Now lambda 1, for random lattice, we understand it is exponential tail. So if you have that number of experiments, you expect the maximum to be roughly n squared log n. Roughly, or we don't get a q, by the way. You get n squared log n in this heuristic. So maybe this is some reason why would you expect polynomial growth. You have just only n squared degrees of freedom. So why would you get exponential improvement? Okay, so this is about, yes, please.
You said that argument suggests a possible bound of n squared log n, and your theorem is about n squared.
Yeah.
Is there any chance of bringing those closer together?
So yeah, I have an ongoing project with Nihar Gargava, what you mentioned earlier, and we think that we can squeeze log factor in some dimensions, but not log yet. So yeah, we don't see a way to get log. Log is all right, but log we don't have no. But it's not written yet. I don't promise anything. Okay. More questions? So now, from now we discuss methods, not only results. So how would you prove anything about packing of lattices, non-lattices? What do you do? So let's introduce officially the space of lattices Xn. All lattices of covolume 1 in Rn. It's a smooth manifold dimension n squared minus 1. But it's non-compact. You can have lattices of covolume 1 that degenerate, right? You can have they can have very, very short vectors and they can be wide in other directions. So they can degenerate to something almost lower dimensional, which means that the space is non-compact space. Still, it's a very nice space. For example, it's a homogeneous space. We have a transitive group actually on that space. So lattices are linear images for one another. So this means that the group SL and R, all determinant 1 linear transformations, act transitively on this space. And if you have a transitive group action, you have a Haar measure. This was known. And the thing is that since it's a non-compact space, a priori you don't quite know if the Haar measure would have infinite volume or finite volume. But Minkowski computed the volume of the space of lattices, and Minkowski and Ziegel discovered that actually there is a unique Haar probability measure on the space Xn. So this is, I mean, when I discovered this measure, I was really feeling, it's such a beautiful measure. There is a God-given probability measure, which is uniform probability measure on the space of lattices. You can flip coins and get a random lattice of covolume 1 in Rn. But it's not entirely obvious that you can have such a distribution over lattices in Rn, which is invariant under linear transformation. So you take a random lattice and you apply any fixed linear map. It's again uniform distributed random lattice. It's quite strong. And just this fact, just this property that there is a Haar measure, there is a unique rotation invariant probability measure on this, not rotation invariant, unique SLN invariant, unique invariant probability measure on this space of lattices, or this fact, just the existence and uniqueness give you immediately interesting conclusions. For example, Ziegel summation formula. Ziegel in the 1940s, he proved the following. Let L be a random, so we have this notion of a random lattice. Now, fix some test function f, continuous comprehensible function, and let's take this random lattice L and let's sum this function f over the vertex of the lattice. Non-zero, I don't like zero. Okay? Now take the expectation, zero is in all of them, so you don't want it. Now take the expectation of this random variable, the sum of the function over the lattice vectors. Well, this is just the integral of f. As simple as that. And why does it make sense that this formula holds true given the existence of the Haar measure? This is because of the following fact. So what happens if you compose f with some linear map SLN, f composed with t? Then you can move this f of t, it's like f of tx, you can move the t to the lattice L, but you say it's invariant, so you can erase the t. So this means that the left-hand side is a functional on these continuous functions, which is SLN invariant. And there aren't that many functional on L1 or on continuous completely supported functions that are SLN invariant. It's basically the value at 0 and the integral. So it must be some linear combination of these two. We excluded 0, so there's no f of 0. And if you just look on scaling, by kind of counting how many points in a region, you can see that the constant that does not appear is 1. So indeed, there is no need for any constant, and you get pretty much this formula. So this is a very nice property. And now let me prove for you the Minkowski bound. How did Minkowski construct a lattice that gives you sphere packing sphere packing of density 2 to the minus n? How do we prove the Minkowski-Klavka bound? So that's a beautiful manifestation of the first moment method, the probabilistic method, that became a big thing with Erdős and many other people. So let me prove this Minkowski-Klavka bound. We claim that delta bar n is at least, let's say, 1 or 2 or some constant factor. What do we do? So let's fix a Euclidean ball B of volume slightly less than 1, 0.99. Fix unit ball of volume 1 centered at the origin. And let L be a random lattice. Now let's look at the expectation of the number of points from the lattice that lie inside B. We never take 0, only on 0 points inside B. This is like summing the indicator of B over all non-lattice vectors. That's the same thing. And we take the expectation. Now, by the Ziegel summation formula, by the way, it's L1. You can. It's not a big deal. It's not continuous. It's just true for L1 functions. You can, from the Ziegel summation formula, this expectation will be the integral of 1b or the volume of b, which is at most 1. But this random variable is the number of points, so it's it's an integer valued, non-negative random variable. It's either 0 or at least 1, but the expectation is smaller than 1, so this random variable has to vanish somewhere. That's the proof. If it vanishes, we found the lattice L, which is disjoint from a ball of volume 1. A ball of volume 1 is huge. It's not, this is unit volume. Ball of volume 1 is root of n. It's huge volume. Sorry, not volume 1, but huge radius, root of n, and no lattice points enter this thing. So that's Minkowski proof. And the factor 2 you get because points come in pairs. So this is an even random variable. That's it. Okay, any question about the Minkowski proof? I mean, if you remember one thing from this lecture, I would focus on this. Okay, yeah, okay. No questions about this? Now let me move on to the Rogers proof. Rogers got a factor of n. How did he do it? The idea is that the Ziegel summation formula indicates that some statistics of a random lattice of covolume 1 are similar to those of a Poisson process of intensity 1 in Rn. What's a Poisson process? This is a much simpler process to analyze. You just, at any region in space, the number of points is independent of any other region in space, which is disjoint. And it's like any tiny piece of space, you put a point there in a probability that equals its volume. That's roughly and they are independent of each other. That's a Poisson process of intensity 1. A highly process with lots of independence in it. And in this theorem, if you replace L, this random lattice, by something much simpler, so replace L by P. P is the point in a Poisson process of intensity 1. This is still true. So some statistics of L are like those of the Poisson process. That's very nice. This gives us a way to at least form conjectures very quickly. So if, for example, let's do the following thing. So if you have a random lattice L of covolume, let's normalize to have the volume of the unit ball. It's another normalization. We enumerate the points in the lattice according to distance from the origin, x0, x1, etc. So x0 is just 0. And now let's look at the product of lengths of the first n vectors in this lattice, the closest to the origin. For the Poisson process, it's pretty easy to estimate this to get that it's roughly n with dimension n. And then Rogers was able to show that the same holds for the random lattice. So he showed that for a random lattice with good probability 1/2, let's say, there are the product of this length of first n vector is at least n. This is what he showed. And then he's done. Why is done? Because there is the Minkowski second theorem of successive minima, which tells us that this is a kind of linear algebra. It's a deterministic statement. Whenever you have any lattice, you can find a linear map of large determinant, at least this product of xi, such that T of the unit ball is L3. So if you just take this ellipsoid, which is T of Bn, you just immediately get this bound by Rogers at delta n is at least n. So this is roughly the Rogers proof that gives you a linear dependence in n. Now, Rogers proof is very, very nice, and it was approved along the years. But you can see that there is some points there which seems to be non-optimal. This is the fact that in the Rogers proof, we don't interact with all of the lattice, but we kind of only interact with the n shortest vectors of the lattice. This is the only thing that is important in that proof. But an ellipsoid is determined by n square over 2 parameters, right? I mean, an ellipsoid is a matrix, roughly, it's a symmetric matrix. And to have a point on, say, on the boundary of an ellipsoid is just one equation on this matrix. So you kind of expect that there should be a construction as interact not just with shortest n vectors, but with kind of n square vectors from the lattice. This is an important point for what is to come. Moreover, there are ellipsoids, it has been known for ages, that there are ellipsoids in Rn, centered at the origin, which are integer free, that have n square integer vectors on their boundary. So if you don't count volume, but you count number of lattice points on the boundary, if you use this as a proxy for volume, then it's really easy to construct ellipsoids with many, many boundary points, many lattice points on the boundary. Let me explain to you a very robust method for constructing ellipsoids with this property. How would you get such ellipsoids? So there are better constructions, but let me give you some things that you could play with. So we have some lattice L in Rn, and we want to find an ellipsoid with many contact points with this lattice, which is L3. No lattice points inside the ellipsoid. What do? We start with a small ellipsoid, which is L3, and we deform it continuously in the space of ellipsoids. Okay, this is what we do. But the deformation has one crucial property. We want to keep the ellipsoid L3. So we impose a condition. Whenever our revolving ellipsoid E sub t, whenever it hits some non-zero lattice point, it would keep it on its boundary at all later times. Okay, so this condition ensures that no points get inside the ellipsoid, that the ellipsoid will be L3 at all times. Now, if ET, the ellipsoid ET, is determined by this matrix capital AT, so the ellipsoid will deform ATXX more than 1, where AT is positive, definite, and symmetric, the condition that we require means the following. It means that if we hit the point x0, so it means that ATX0 times x0 equals 1 at time t0, we require that for any larger t, we still have this equation. And we evolve the ellipsoid ET, or if we evolve the matrix AT, and that condition is a linear equation on AT. So we can continue the evolution of AT in the orthogonal complement, in the subspace, linear subspace of affine subspace of matrices satisfying this constraint. So we just get lower dimensional subspace whenever we hit a boundary point, whenever we hit a lattice point. Okay, so this process would continue in the, would continue as long as we have degrees of freedom to move. And since each point gives us just one linear constraint, let's ignore the fact that everything will be positive definite, it's guaranteed somehow. Don't ignore the fact that it's symmetric, but each point gives you one linear constraint, so it means that you can continue again, until you run out of all degrees of freedom, and degrees of freedom is n times n plus 1 over 2, so you'll get, in this process, you are guaranteed 100% to stop when you have n times n plus 1 points on the boundary at least. Let me show animation. So we start with the unit ball, okay? It's open set, so these green points are not in the tree of the ellipsoid. And we deform it, we let it grow, and now it got more points on the boundary. So, okay, in this case it is stuck. There are no 6 is the maximum dimension 2. But in general, in high dimensions, we grow such an ellipsoid continuously, and we'll stop not it gets 6 points, but it will get n square boundary points. Any continuous process will give us this thing. Okay, so this is very good. You are guaranteed any process, continuous process like this, is guaranteed non-trivial, is guaranteed to be L3, and we are guaranteed to have n square lattice points on the boundary of this ellipsoid. Okay. But the problem is not about number of lattice points on the boundary, the problem is about volume. What is the volume of this ellipsoid? How can we trade having lattice points on the boundary with having large volume? Now the Poisson heuristics comes to our rescue, okay? Just in order to understand what's going on, I throw away the lattice L and I replace it by a Poisson point process, just random points in Rn, uniformly, kind of intensity 1. And let's try to understand what would happen in our process if we replace L by P. A Poisson point process, let's remember, it has the number of points is the expectation equals the volume, so it is expected to have only 1 point per unit volume. That's it. And as a nice thing with the Poisson process is that it has lots of independence. So we don't have really to decide in advance about the entire Poisson process. Only whenever the ellipsoid arrives in some new region in space, we can flip the Poisson process coins and decide whether or not there are points in this region. Okay, only in regions that the ellipsoid encounters. Whenever it encounters a new region in space, we sample the Poisson process there. This is a possibility. This means that our ellipsoids, we know that it encounters n square points from the discrete set. But in the Poisson case, in order to encounter n square points from the discrete set, you must cover a volume of n square. Okay, so you must, I don't think that you stay there, but if you don't touch volume of more than n square, you have no chance to see n square points of the Poisson process. So we know that in a very general situation, pretty much any non-trivial continuous process, when you run it on the Poisson process, related to the Poisson discrete set, we know that not only it would have n square points on its boundary, but we also know that it kind of, in total, the union of all ellipsoids would have volume at least n square. So that's a really good sign. Like it means that we have lots of flexibility because we said nothing about the continuous process, okay? And of course, there are some issues. For example, the ellipsoids is not increasing. It expands and contracts. We have some linear equations on AT. But you can hope that you can manage to do something, okay? So this is the heuristics that is going to guide us in the proof. Let me just tell you that the Poisson heuristic has lots of limitations. For instance, if you replace L by P and just look at the original problem, you say, what's the largest volume of an ellipsoid centered at the origin, which does not contain points from the Poisson process? Then the volume is infinite. I mean, it's not bounded at all. So it's not the same problem. And for this, you get n square. So it's not that you can always replace lattice by Poisson. So you need to have something kind of basic enough that would not distinguish between the Poisson and the lattice. I mean, if you have events that depend only on 1 point, it would work. Or at most, if you have events depending on more than n points, it would not work because you have some linear dependencies. But kind of events that do not depend on many points, it should work, and maybe something very simple. That's our idea. Okay, so now let me tell you how to transform this kind of vague heuristic of evolution of the ellipsoid into a mathematical proof. So let's begin with a fixed lattice L. I prefer in my construction to separate the randomness into 2 parts. We'll have randomness coming from the random lattice of Minkowski-Siegel, and we have another randomness that would come from some Brownian motion. And just easy for me to separate these 2 sources of randomness. But for now, let's assume that the lattice L is fixed. Its covolume is the volume of the unit ball, and it is disjoint from the unit ball. I mean, it's not really units, 1 minus 1 over n, but let's separate it roughly the unit ball. N is large number, so you can find, we know that for random lattice with good probability, you are disjoint from this almost unit ball. So we start with this lattice, which is fixed now. And it is disjoint from the unit ball, so we start with this unit ball. And now we want to find some continuous evolution process starting from this unit ball. which process will we choose? We have this matrix AT, and we need to deform it continuously. And if you have nothing better to say, then just take some random thing, some Brownian motion. This is what we do. We look at the space of symmetric matrices. This space is a Euclidean space with this, the metric is trace, this, So that's the usual thing to do. So AB is the trace of the product. Maybe I can put a transpose, although it's not needed. They are symmetric matrices, just so you recognize it. So that's a Euclidean space, and there is, on a Euclidean space, you have a Brownian motion. In this particular case, it's called the Dyson Brownian motion. Okay, so we run the Dyson Brownian motion in the form, the matrix AT. At time 0 is starts with identity. This is just 1. This is roughly 1. So you have the Euclidean unit ball, and you deform this matrix continuously. Okay, and you get the ellipsoid ET determined by AT. Okay, in the form continuously, and then you have to stop. When do you have to stop? We have this requirement. When you see a non-zero lattice vector on your boundary, you have to keep it on the boundary at all later times. So tau 1 is the first time when you encounter a non-zero lattice vector. Okay? And then what would you do? You look at the space of all matrices that satisfy these constraints, that are orthogonal to the constraint, and then you can continue the evolution only in the subspace orthogonal to the constraints. So in the next steps, we will take the white noise, we'll take the Brownian motion and project it onto the space that is orthogonal to the constraints, into the space of all allowable movements. Okay? And then we have many phases. At each phase we stop when you see another point, and the space of allowed movements, Ft, gets smaller and smaller and smaller with time. The projection gets smaller and smaller and smaller and smaller. We are guaranteed to be L-free. No lattice points can enter our ellipsoid. You get many, many points on the boundary. And we stop when pi t is just 0. So when pi t is 0, it means that AT does not change, and we stop. Okay, so this is our process. We are guaranteed to have at least n square lattice points on the boundary. Many contact points with the lattice we're guaranteed. By the way, the number of phases is finite. This is a really bad upper bound, but it just works. I mean, okay, so the number of phases is finite, and we freeze. Okay, so this is the exact construction of the ellipsoid that we will use. And now we need to analyze this stochastic process of ellipsoid, and we need to show that it has a large volume. Okay, that's what we need to do. I will not run this process till infinity. In principle, I should run it till infinity, but for analysis, it's easier to stop the process at some time. I prefer to stop it at this time, okay, in my normalization. So it seems quick, but it's just a matter of scale. In order to get some insight for this number, let me tell you why did I choose this number. Because we'll analyze how many lattice points your ellipsoid absorbs from the lattice, and the expected number of lattice points up to time t is exponential in t with exponent n squared over 8, as it happened. So this is at most, this is just an upper bound for the number of lattice points on the boundary. And if you plug in this number, capital T here, you should get e to the 2 log n, so you get n squared. Okay, so I stop my evolution when I estimate that I already accumulated n squared lattice points on the boundary. Okay? And the only thing that remains to be proven is this proposition that with the process I described to you, this capital T, the determinant of AT is very small, at most 1 over n to the 1 over n to the fourth, 1 over n to the 4, so n to the minus 4. That's the determinant of AT. Why n to the 4? Because the volume of the ellipsoid is 1 over the square root of the determinant of AT. So this will be n squared if this is n to the 4th. So this is what we need to do to analyze this well-defined process and get this bound. In our head, what guides us is what happens with the Poisson. So the Poisson, you can write down quickly some estimates and get things, and our hope is that it will be the same for us too, and apparently it is possible. In the proof, you don't write Poisson, it's not used, but kind of in your head, you make sure that it's the same. Okay, so let's say a few things about this process AT. So the matrix AT, first of all, why it's always positive definite? That's because the ellipsoid ET, it avoids odd lattice points. So by Minkowski's theorem, its volume is bounded by some 2 to the n times the determinant, by some number. And if you have family of quadratic surface, if the ellipsoid would degenerate, in the way to, if the matrix becomes indefinite, then at some point you will have infinite volume. This ellipsoid will become a quadratic surface of infinite volumes, which is not allowed. So we are guaranteed by our process never to leave the cone of positive definite matrices. So AT is always positive definite and symmetric, okay? The matrix process AT is a martingale because we had just white noise, Brownian motion, and sometimes we project it linearly, so still we had sinks of expectation 0. And what is the quadratic variation of this martingale? Since we just project, the quadratic variation of this martingale AT is at most the quadratic variation of this plain vanilla Brownian motion, of the Dyson Brownian motion, because you only get smaller variation. Okay, for a martingale, all you want to understand usually is it's how much martingale is kind of goes up and down, and the speed in which it goes up and down is the important thing. And the speed is the quadratic variation. So it's kind of slower. It goes up and, I mean, it's a matrix, but it kind of goes up and down in a way which is not faster than that of the Dyson Brownian motion. Okay. Now comes a beautiful fact that is attributed to Bernard Moret. And this is the following fact. So whenever you have any martingale, think of dimension 1, not a matrix. Think of martingale whose quadratic variation is slower than that of the Dyson Brownian motion. Yeah. So for a function, quadratic variation is just you take a small partition and take the so for a so if you have a function, what's the quadratic variation? You take partitions. You take the limit. You take partitions of on interval is 0b. So you take sample points where the maximum tends to 0. So where xi plus a plus m plus 1, like in Riemann integral, these things, the maximum tends to 0. And you just sum f of xi minus f of x minus the sample point squared. So for example, for a smooth function, this is just 0, right? However, Brownian motion is a Hölder-Haff function. So for this random variable, actually tends to the length of the interval for Brownian motion. Okay, so this is called the quadratic variation. It's how fast things change for the martingale. And when you have a martingale, that's the thing to, I mean, that's the kind of, in dimension 1, this pretty much characterizes the martingale. That's all of them are kind of time change of a Brownian motion to this quadratic variation thing. This is quadratic variation. So if you don't know what it means, okay, all you know is that this is less wild than Brownian motion. And as it turns out, whenever you have such a martingale, which with a quadratic variation which is not too large, it is maybe expressed as the average, just arithmetic average of two dependent Brownian motions. It's pretty strange, right? But for example, if 8 is just constant, if it has 0 quadratic variation, does not move at all, then you can take a Brownian motion and take minus of the Brownian motion. So these are two dependent Brownian motions. Their sum is 0. So this works. And it works for whenever you have kind of a partial order if you want. So whenever you have quadratic variation is bounded, you have this property. So our martingale is the average of two Brownian motions which are dependent. This is very helpful. Why? Because Brownian motions are easy to analyze. You don't have any lattice. If you look at a given time, you get GOE matrix, and you can estimate the norm easily. And for example, it's pretty easy just by looking at the probability. So what's the probability that AT would deviate from the matrix by more than something? You say, each of these Brownian motions usually does not deviate by much. So you get a factor of 2 and you get roughly the same probability estimate. So you can easily get that your ellipsoid is sandwiched between two concentric rectilinear balls of some radii because AT does not move that much from the origin. So our process, the ellipsoid that we find, is pretty close to a Euclidean ball. Only a small perturbation of the Euclidean ball, that's what we'll get. This geometric bound is not enough to estimate volume, and we need to understand the evolution of the determinant of AT, log det of AT, how does it change? Here comes another nice fact to our rescue. Log det is a great function on the positive definite cone. It is a concave function. Concave means that if you have a martingale, if you take the average of the values at 2 points, okay, it will be smaller than the value at the original point. So log det should go down just because you're a martingale, and you can pretty much go down as fast as the dimension of space of possible movements. So using Ito calculus, not that difficult, really simple application of the Ito formula, you'd get that the expected of log that of AT goes down in a linear pace, like you would get for a Brownian motion, but you pay fine because you don't have all movements, so the fine that you pay is just the expectation of the number of lattice points on your boundary. Okay, so now we need to understand what's the rate at which you absorb lattice points. Again, we use this fact that you're the average of two Brownian motions, and for a fixed point, you could estimate when would be absorbed by the ellipsoid. You say, aha, I have this, the martingale ATX x minus 1. It's the average of two Brownian motions. So one of them should vanish in order for the average to be 0, and you get some estimate which is in terms of standard Gaussian, in terms of standard Brownian motion, for the ability to absorb a given point x in Rn. By linearity of expectation, you can say that the expected of the total of contact points of your ellipsoid is the sum of the probabilities. Each of them is bounded by phi, is the error function of something depending on the Euclidean norm. So you know that the expected number of contact points is at most this sum. You only look at points in the thin shell where the ellipsoid lives, because we know that the ellipsoid does not leave some region usually. And now we need to understand this sum here. This is exactly the sum from the Ziegler summation formula. We know that for the random lattice, this sum is just an integral. So that's the first place in the proof when we say what is L. L is a random lattice, and in expectation this will be some integral of a radial function. Integrals of radial functions are polar coordinates. This is one-dimensional integral. It's not so complicated. So we get that the number of contact points behaves as I told you, and this proves the theorem. Okay, so this ends the proof. It could be that we can squeeze a log factor, I don't know, by using something more sophisticated, but no, I was not able to do it. Yeah, so this is it. Thank you.
Given that we're over time, how about just one question? I guess. Yeah, Pavel. One second.
So you considered this linear Brownian flow for the matrix A,
Yeah.
T. But A is a positive definite matrix, so it is like maybe it seems more natural to work with log A and consider flow for log A. Then, for example, it would be automatically positive. You don't have to. So why are you using the flow for A and not log A? It doesn't matter, or so?
Okay, so you said that the positive definite cone is Riemannian manifold. So what you suggest is to use the Brownian motion of the Riemannian manifold.
Yeah. Negative curvature. Negative
Ricci. Even scalar. Yeah, non-negative. Okay, at least non-positive. Right. There are some. Yes, this sounds like more natural from the point of view of intrinsic geometry, right? But it's much harder to analyze. I mean, this is a process I just cannot analyze. And adding to A pure Brownian motion, it's much easier to analyze. You have this average of two Brownian motions, just much better. You also need very short amount of time. So you would not reach any invariant problem. It will not reach anything. So yeah, this is an obvious choice to have something more intrinsic, right? On the space of lattice. In fact, you could also just work the space of lattice. Why do you need lattice and ellipsoid? Take a random lattice and let it evolve in the space of lattice, which is again this is the same construction. Somehow it's impossible to analyze for me. That's what happened. It matters a lot. Like it's not.
Okay, let's thank him again.